Thanks everyone for attending this talk. My name is Udit and I'm a fourth year PhD student at Harvard, and today we're going to talk about the challenges and interesting opportunities for optimization available when looking at at-scale inference for recommendation systems. Personalized recommendation is the task of recommending new content to users based on their personal preferences. Personalized recommendation algorithms are found across many internet services that we use on a daily basis. For instance, it enables Netflix and YouTube to recommend what videos we might want to watch next. It is used by Amazon and Alibaba in suggesting what products we might want to buy next. And it powers how Facebook ranks social media posts that show up on our newsfeed. In fact, recent estimates show that 35% of purchases on Amazon and 75% of videos watched on Netflix are powered by recommendation algorithms. Now, given this economic impact, modern methods for recommendation are starting to use deep learning solutions in order to improve user experience by providing higher personalization. Now, in addition to this economic impact, we find that optimizing neural recommendation is key for improving data center efficiency. So here we're looking at the breakdown of AI inference cycles within Facebook's data center. In red, we see the cycles devoted to non-recommendation use cases such as vision and NLP, which account for about 20% of all AI inference cycles within Facebook's data center. Highlighted in blue are the cycles devoted to recommendation use cases. Aggregating these recommendation use cases together, we find that recommendation accounts for over 80% of all AI inference cycles within Facebook's data center. Given Facebook's data centers perform over 200 trillion inferences every day, optimizing DNN-based recommendation is key for improving data center efficiency. Now, given the importance of these workloads, we find that co-designing algorithms and hardware solutions is crucial for realizing efficient and scalable neural recommendation systems going forward. In this talk, we will first start with an in-depth workload characterization using Facebook's DNN-based recommendation models. Next, given the intuition gained from this characterization, we'll briefly look at DeepRecSys, a system to optimize end-to-end at-scale neural recommendation inference. First, in this talk, we will conduct a detailed workload characterization of the recommendation models with a particular focus on Facebook's DNN-based systems. In particular, we will highlight the key hardware insights and exciting opportunities for future system optimizations that we found by studying the different aspects of recommendation algorithms. First, we will look at the key building blocks of recommendation models and find hardware systems must optimize operators with new storage, compute, and memory access patterns. Next, we will look at end-to-end network architectures for recommendation and find accelerating recommendation models requires flexible and diverse system solutions. And finally, looking at how recommendation models are deployed to process queries at scale, we find exploiting hardware heterogeneity and different forms of parallelism can optimize for latency-bounded throughput. First, let's look at the key building blocks in recommendation models. To better understand the unique characteristics of recommendation, let's take a look at an example. Here we have an e-commerce platform where the goal is to determine which books to recommend the user to buy next. However, before we can answer this question, we must first ask, what is the likelihood the user will like a particular book? In this case, the first installment of the Harry Potter series. The decision is made using a set of continuous or dense, as well as categorical or sparse input features. Now, examples of continuous or dense features are inputs such as the age of the user or the time of day that the user is interacting with the e-commerce platform. Dense features are processed by a set of dense DNNs, such as MLPs or fully connected layers. On the other hand, examples of categorical or sparse input features are things like the user's purchase history or the book's genre. Categorical input features are represented as a set of multi-hot encoded vectors. For example, in the case of the user's purchase history, a 1 represents all the books the user has visited in the recent past. Similarly, a 1 in the book's genre represents different identifiers for the book. In this case, we can describe Harry Potter as having both magic and being part of a series. Note that the size of the vector is set by the total number of categories, which ranges from up to tens of millions of entries in production workloads. However, users only sample a very small subset of the total items in this space. This means that the multi-hot encoded vectors are not only large, but also incredibly sparse. Now, given operating on such sparse data is difficult, we must first transform the sparse inputs into dense ones. One way of accomplishing this is using embedding tables. The key idea is that entries in the multi-hot encoded vectors are used to index rows within the embedding table. These lookups result in dense embedding vectors, which represent the learned feature representation for each of the categories. The intuition here is that categories that are more similar to one another will be found closer together in the learned feature representation space. For example, here we see that Inkart and the Hunger Games are found closer together in the learned feature representation space as opposed to Moby Dick, which is a very different type of book. After performing this lookup, the embedding vectors are aggregated together using different operations such as sum or averaging. The aggregated embedding vectors are then combined with the output of the dense DNNs. And finally, a stack of predictor DNNs produces the likelihood the user buys or likes a particular book. In this case, we find that the user has a 90% chance of liking the Harry Potter book. The red box here annotates the overall DNN-based recommendation model that is used to rank the probability that the user positively interacts with an item. However, it is important to note that this is for a single book. In the case of production use cases, we find that recommendation systems typically have to rank potentially tens of thousands of books or items that could be presented to the user. Now, to reduce this range down to a handful of recommendations for the user, production systems implement a multi-stage ranking process. First, we apply a filtering process that uses smaller scale DNN-based recommendation models to filter down the possible items down to a few hundred. This model follows the same high-level architecture that we saw earlier. Following the early stage filtering process, larger recommendation models are used in the later stage ranking processes in order to produce a few likely items that the user may purchase. Now note that these ranking models also follow the same high-level network architecture that we saw earlier. Typically, the user's interactions, along with the suggested recommendations, are used to periodically train and update the recommendation models used in production systems. Now, for the purposes of this talk, we will focus on the inference stages of recommendation models. In particular, note that the end-to-end multi-stage ranking process requires processing tens of thousands of individual items using a variety of recommendation models. To address these compute demands, production data centers often exploit both data level and task level parallelism for serving recommendation at scale. Here we will characterize the design space of data level and task level parallelism a little bit later in the presentation. However, central to both the filtering and ranking recommendation models is the idea that they must process both categorical as well as continuous input features. In fact, In order to process these categorical input features, we find that they use embedding table operations, and that these embedding tables pose many new challenges that require us to rethink system and hardware designs going forward. First, we look at storage capacity. Here on the vertical axis, we consider typical RNN, FC, and CNN layers, as well as a typical embedding table operation found in a recommendation model. On the horizontal axis, we measure capacity in megabytes. We find that the embedding table operations have orders of magnitude higher storage requirements. In fact, production models often require up to tens or hundreds of gigabytes of storage. Next, we consider the compute intensity of embedding table operations. On the vertical axis, we have the same operations, while on the horizontal axis, we measure the compute intensity in terms of flops per byte. We find that embedding tables have orders of magnitude lower compute intensity compared to typical CNN, FC, and RNN layers. Finally, we'll consider memory access patterns. On the horizontal axis, we have cache miss rate measured as MPKI. Once again, given their sparse and irregular memory accesses, we find that embedding tables have orders of magnitude higher cache miss rates. Now, given these unique challenges, we find that systems and hardware solutions must consider unique characteristics of embedding tables in order to optimize end-to-end execution of recommendation models. Now, some of these opportunities include considering off-chip memory systems such as DRAM and non-volatile memories. Solutions may consider new accelerator designs such as near-memory computing. And finally, they may also consider specialized caching and prefetching capabilities that are customized specifically to the recommendation use cases. Now, in addition to considering key operators within recommendation models, we look at the end-to-end network architectures. To study recommendation models, we use an extensible implementation of Facebook's deep learning recommendation model. This implementation can be used to sweep different parameters of recommendation models in order to analyze their impact on system performance. For example, the compute intensity of the model can be set by varying the number of input dense features, as well as the width and depth of both the dense DNNs and predictor DNNs. Note that these computations can be readily accelerated by many of the hardware proposals designed for vision and NLP use cases. On the other hand, processing categorical input features with embedding tables, as we saw earlier, poses new challenges. In particular, the storage capacity of the model is set by the number of input sparse features, as well as the size of the embedding vectors and the number of embedding vectors per embedding table. In fact, in production scale models, we find that these embedding tables consume tens or hundreds of gigabytes of storage. Finally, the degree of irregular memory accesses, which determines the memory bandwidth requirements of these models, is set by the number of multi-hot encoded lookups per embedding table. Now, in order to study the end-to-end network characteristics and the performance implications of these models, we study representative examples from three key classes of recommendation models. In particular, we look at RM1, 2, and 3 that consume over 60% of all AI inference cycles within Facebook's data center. Here we see the key differences across these three recommendation models. In particular, we find that RM1 is used in the early stage filtering processes, while RM2 and RM3 are used in the later stage ranking processes. This means that RM1 is orders of magnitude smaller than RM2 and 3 in terms of the FC sizes, as well as the size and scale of the embedding table operations. Here we look at the inference latency of these three model types with a unit batch size. So on the x-axis, we have the three models RM1, 2, and 3, and on the y-axis, we have inference latency. We find that inference latency across the early stage filtering and later stage ranking model varies by up to 15x. Taking a deeper dive, we find that the three models have a variety of different operator bottlenecks. Here, we see the same three models on the x-axis, with the operator breakdown in terms of the percent runtime on the y-axis. We find that RM3, a late-stage ranking model, spends the majority of its time processing the compute-intensive fully connected layers. This is a result of having large, dense DNNs within RM3. On the other hand, RM1 and RM2 spend a significant fraction of their time processing embedding table operations, shown as blue over here. In fact, RM2, another late-stage ranking model, spends almost 80% of its execution time processing embedding table operations. More generally, given the varying performance characteristics, we find that diverse system solutions are needed in order to optimize the diverse set of recommendation models. Next, we will look at how recommendation models are deployed to process queries at scale. One of the key aspects of recommendation is that ranking more items leads to improved recommendation quality. And this improved quality leads to better user experiences. Thus, in order to rank more items, we find that recommendation systems must be designed for incredibly high throughputs. However, in order to preserve user experience, recommendation inference must also meet strict latency targets. By balancing both high throughput and low latency, we find a key new optimization target. That is, recommendation inference is optimized for latency-bounded throughput. Here, we want to characterize the design space available to maximizing efficiency in recommendation centers run in the data center. We find that to maximize the latency-bounded throughput, solutions must co-design across three key aspects of neural recommendation. The first is the diverse set of recommendation models that we saw earlier. The second is a heterogeneous set of hardware platforms that the models can run on. Now here, we're going to consider three server-class CPUs, such as Intel Haswell, Broadwell, and Skylake. This is a result of the DNN-based recommendation models requiring large irregular memory accesses and storage requirements. As a result, Facebook's DNN-based recommendation models are typically run on server-class CPUs. Now note that these hardware platforms have unique clock frequencies as well as compute intensity and memory hierarchies. Finally, we find that solutions must also consider different forms of parallelism, such as data-level parallelism and task-level parallelism. First, we will consider data-level parallelism. Here we look at the performance of RM2. On the y-axis, we have batch latency, where lower is better. And on the x-axis, we increase the amount of data-level parallelism on the Broadwell architecture by increasing the batch size from 16 to 128 to 256. At each batch size, we can also study the performance across the three server-class CPUs, such as Haswell, Broadwell, and Skylake. As expected, strict low latency targets are met with smaller batch sizes. At these smaller batch sizes, we find that the Broadwell architecture provides a 1.4x performance improvement over the Haswell and newer Skylake processors. This is a result of Broadwell implementing a higher clock frequency as well as having higher utilization of its AVX256 instructions compared to the newer Skylake processors. On the other hand, If we consider applications with more relaxed latency targets, such as social media, in order to maximize the number of items that are ranked and thus the quality, we find that Skylake is the optimal architecture. This is due to the wider AVX width, which has higher utilization with the larger batch sizes. And we find that these trade-offs depend heavily across the different model architectures considered for the recommendation space. However, more generally, we find that solutions that optimize the latency-bounded throughput must co-design across data-level parallelism, the application target, recommendation models, and the underlying hardware platform. Next, we consider task-level parallelism. Generally, we think of co-locating applications in the data center. We classify them as either latency-critical or batch processing applications. So here we consider a fixed workload latency-critical application running on two separate servers. Now, given the application's significant slack in meeting the target tail latency, we co-locate batch processing applications in order to more fully utilize the server's capabilities. In the context of recommendation models, inference is also bounded by a strict latency target. However, we find that we have an additional knob to exploit in order to fill this latency slack. Namely, we can increase the amount of work processed or items that are ranked. This can be accomplished by co-locating multiple models onto the same server. Qualitatively, this enables ranking more items, which leads to higher recommendation quality, as well as increasing server utilization, which reduces the total infrastructure capacity that is required to process recommendation at scale. Now here, let's take a deeper dive on this trade-off. Here we look at a single model, the RM2 model, running on a Broadwell machine. On the y-axis, we vary the tail latency target, and on the x-axis, we measure throughput where higher is better. Across the curve, we increase the degree of co-location by increasing the number of models that are simultaneously running on this Broadwell architecture. Now, intuitively, by increasing the degree of co-location, the latency of any one model degrades, however, the overall system throughput improves. Here we have the same plot, however, with Haswell in black and Skylake in green. Following the earlier results, we see that Broadwell is a latency optimal hardware platform. This is a result of Broadwell having a higher CPU frequency and implementing a simpler inclusive cache hierarchy. On the other end of the spectrum, by increasing the latency target, we find that Skylake achieves the highest throughput. This is a result of having a wider AVX width and implementing the exclusive L2, L3 cache hierarchies. In particular, we find that with the exclusive cache hierarchies, not only is the absolute L2 miss rate lower on the Skylake processors, but it also increases by a smaller amount compared to the Broadwell processors. Now, given the irregular memory access requirements of these recommendation models, we find that this is key for the Skylake processors in order to enable a higher system throughput. More generally, we find that in order to optimize the overall latency-bounded throughput across this design space, solutions must consider both data and task-level parallelism, along with the application targets, recommendation models, and underlying hardware platforms. In order to enable researchers to explore these trade-offs, Facebook has recently open-sourced a deep learning recommendation model used in this study. On the left here, we see the same high-level network architecture, where you can specify the varying characteristics of the model, such as the depth and width of the bottom and top FC layers, as well as the number of rows and columns of the embedding tables and the number of embedding tables, and the number of multi-hot encoded lookups for each embedding table. To configure these parameters, here we show a sample command line argument using the open source PyTorch DLRM implementation that you can find on GitHub. We find that the bottom MLP or FC layers has 3 layers with 128, 128, and 64 nodes respectively. Similarly, the top FC layer has 3 layers of 1024, 256, and 64 nodes respectively. An example embedding vector dimension is 64, where each embedding table has 2 million rows and 100 lookups per table. Finally, we can specify different datasets, such as the open source Criteo dataset. Now, to guide inference studies, our characterization also provides locality analysis for the different production traces found in Facebook's recommendation use cases. These can be instrumented with DLRM's synthetic trace generator in order to model some of the use cases found in Facebook's production data centers. Note that Maxim will cover how to use DLRM for training personalized recommendation systems in the Training Deep Learning Recommendation Models talk in the personal tutorial program. Now, given this initial characterization, we will now briefly talk about some of our upcoming work on optimizing end-to-end at-scale neural recommendation inference. The infrastructure first implements a load generator that samples query arrival and size distributions based on characterization of Facebook's production data centers. The load generator then produces queries that a scheduler determines how to process in order to maximize efficiency. For example, the scheduler can send the query to be processed or run on an accelerator platform, or it can decide to split the processing of this query across many CPU cores. Finally, these queries are processed by a variety of neural recommendation models running on these back-end hardware platforms. Here we highlight the different key aspects of the deep RecSys infrastructure. Using this infrastructure, we can co-design across the different application level use cases, different forms of parallelism, different hardware platforms, and finally, the different model architectures. The key takeaways from deep RecSys are that in order to optimize for latency-bounded throughput, or power efficiency, which is measured as Inference QPS per watt, systems should co-design across each of these key aspects. This includes the algorithms or underlying recommendation models, underlying hardware platforms where we consider server-class CPUs as well as AI accelerators such as GPUs, different forms of parallelism such as data and task-level parallelism, and finally, different application-level input use cases by modeling query arrival and working set sizes. Now, in order to further enable research into at-scale neural recommendation inference, we will open source the developed infrastructure in the coming weeks. To recap, in this talk, we saw the importance of studying recommendation models in order to improve AI efficiency within the data center. Next, studying end-to-end recommendation models, we found that they have varying and unique performance characteristics that require flexible hardware solutions. And finally, we saw that at-scale recommendation inference is optimized based on latency-bounded throughput and co-designing parallelism, application targets, models, and the underlying hardware platforms can unlock significant performance wins. If you're interested in this work, you can find the open source implementations of Facebook's deep learning recommendation model on GitHub. And with that, I will conclude this talk, and thank you for listening.